Thank you. And thanks for the invitation to speak here. So my main area of research is algebraic geometry, but since about 5 years ago I've also been thinking about logic, and to a large degree together with a former master's student of mine, James Clift. So everything I'm going to talk about, or most of it anyway, is joint work with James. These slides are available on my webpage. You can see at the bottom there, therisingc.org. So what I'm going to talk about is a mix of all of this stuff. This article at the bottom, if you're interested in the topic, is maybe a good place to start. So this is a survey article which presents linear logic, which is the main topic, but from an algebraic point of view. There's many other good introductions to linear logic, including a good one by Méliès, which you can find the reference for in this introduction of mine. Okay, so let me start with the place where linear logic began, which is this article of Girard's. So there's a few ways of motivating linear logic. I guess my motivation is primarily algebraic, and I'll get a bit more into that later. But from a logical or computer science point of view, I think the best way to motivate linear logic is to just remind you about the sort of contrast between Lambda Calculus, which has already been mentioned today, and Turing machines. So these are both, as you all know, formalizations of the idea of an algorithm, and they capture the same class of computable functions, but they're not equivalent in like a stronger sense. So they both produce the same class of computable functions, but there's a sense in which Lambda Calculus is inferior. Let me tell you why. So what's Lambda Calculus? Well, Lambda Calculus is basically a theory of symbols. Right? It formalizes the idea of a variable and of substitution. And Rajiv talked about the beta reduction rule, which is what does that. But here's the rub. If you take a lambda term, which is a kilometer long when you write it down on a piece of paper, but you try to do the beta reduction rule, that is, you've got 1 million occurrences of some variable, and you're supposed to substitute some term for all those occurrences. Well, those substitutions are supposed to happen simultaneously, at least from the point of view of lambda calculus. There's nothing in the theory itself which would distinguish between the state before you made all of those substitutions and the state immediately after you did that one step which made all 1 million substitutions. And that's the exact reason why you can't see complexity from the point of view of lambda calculus. So as far as I can tell, there's two really deep ideas that computer science has contributed to mathematics more broadly. That's computability and complexity. And while lambda calculus and Turing machines have the same answers with regards to computability, on one side in Turing machines, of course, you can talk about complexity. It's basically impossible to locate time complexity, let's say, in lambda calculus, for the reason I just described. It can't see those operations of substitution happening separately from one another. Okay, so that's a defect in the lambda calculus, I would say. I mean, of course, it's good for many purposes, but there's the idea in Turing's original paper, which gave rise to Turing machines, the deep idea is locality, right? The idea that a write or a read happens locally in space. And this idea is missing from the lambda calculus. So I would motivate linear logic in the following way. I would say it's the minimal thing you can do to fix lambda calculus. Okay? So if you fix this problem of substitutions happening simultaneously, non-locally, the minimal way to do that is to produce the refinement that is linear logic. So that's, I'll get more precise later, of course. You can see some comment at the bottom here. This is a bit of an extract from Girard's paper. So this first part here is explaining something like what I just said. The second part here is, if you like, what gave rise to differential linear logic, which is the extension of linear logic I want to talk about. And it's making the comment, basically, that the operation of identification or substitution, which I just discussed, has some formal similarity to the derivative in calculus. That connection is not meant to be obvious, but to an algebraic geometer that makes total sense, because that's exactly how we think about derivations in our subject. So this is one of the reasons I became interested in this topic, because I just recognized this as being just a correct idea from the point of view of an algebraist, and logically it's also sensible. Okay, so I want to tell you what differential linear logic is, but let me start with linear logic, and this is a sketch. I'll give you the deduction rules in sequent calculus style in a minute. But briefly, so for me, linear logic means intuitionistic and first order linear logic. If someone's curious, I can say more about second order and non-intuitionistic linear logic at the end. So what's linear logic? Well, it's a logic. It has types and certain constructors for new types from old ones. Maybe the first I'll describe as the tensor. You should think of this as a sort of refinement of the usual logical connective and there's a linear implication, or lollipop it's sometimes called, which is the sort of refinement of usual implication. And then there's this funny new thing. So this, either called the exponential, for reasons I'm not going to get into too much, or colloquially bang. So bang A, is how I might read it later. Okay, so that's another unary connective. And out of those basic connectives, you can build up data types like integers, like these are church numerals, binary integers. If you're familiar with how you encode data structures into Lambda Calculus, these follow a very similar pattern. Okay, so for instance, I mean, maybe this is a good time to have a look over there. So I've put two proof trees on the board. This is the usual church encoding of the number 2 in simply typed Lambda Calculus. And that guy over there is the same encoding, but in linear logic. So none of that will make any sense right now, but anyway, there they both are. Okay, so this 2 underline is a proof or a term of some type. What is the content of that proof? Well, it's a tree like that, following certain rules, which I'll elaborate in a minute. But that's what this thing is. And for each integer greater than or equal to 0, there's such a proof of this type. The type here is, yeah, maybe that's a bit unfortunate. Let's see, I think it's maybe on a later slide somewhere. Okay, let's not worry about the type of int. Bint I'm going to talk about in more detail. So for each string of zeros and ones, there's a corresponding proof of type bint, and I'll give you the precise formula for bint in a moment. So taking that for granted, there's a way of encoding basic operations on sequences. For example, the function that repeats a sequence is a proof of this type. Now the way you're supposed to read this, and I'm fortunate that Rajiv sort of explained some of this already. So if you read this as an implication, in the sense he was writing it, then this is a function. Repeat is a function which takes an input of type bint and gives you an output of type bint. Then there's this funny bang to worry about, and I'll explain what that means in a second. But, well, you would believe that repeat applied to S should give you SS. That's how you're supposed to think. Okay, so what does that actually mean? Well, here's a proof tree. So here's S. And the dot, 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 this is sort of meant to indicate this is a proof of type bint. Here's repeat. It's a proof of this type, which has a hypothesis or an incoming piece of data, which is a binary integer, and it gives an output of a binary integer. And this is a cut rule. So that plugs this input into this function. Now, the important piece here is that there's an equivalence relation on proofs generated by certain steps called cut elimination steps, under which this cut is equivalent to the proof SS underline of bint, the encoding of the repetition of the sequence. And that's the sense in which this is a function which takes this input and computes that output. Now, let me now say something about what this exclamation mark means. Notice that in the repetition, the output, SS, every bit of the input appears twice. Right? Now, in linear logic, if you have an input which doesn't have a bang in front of it, so if this was just bint, arrow, or lollipop, bint, there would be no way to construct repeat as a proof of that type, because repeat, obviously, uses its input in a non-linear way. It repeats it. So in order to use that input, I need to first apply a deduction rule which takes a proof and promotes it to one that I'm allowed to use more than once. Okay, so this is called the promotion rule. Then I can cut it as an input to repeat, and everything works. Okay, so there's some, the details here are maybe not too important. What I want you to take away is there's types, there's terms, and in the construction of these terms, which you can think of as either data structures or programs, there's this management of using inputs in a non-linear way. Okay, so that's what the unique features of linear logic do. Okay, so that's the brief sketch of linear logic, and as I said, I'll show you the deduction rules and get into the details in a minute. But before I get into that, let me say somehow a word about differential linear logic, or differential lambda calculus. So, foreshadowed by this comment of Girard's, Erhard and Regnier while investigating certain semantics of linear logic, discovered something that looked a bit like a derivative of proofs. And then they formalized that. They sort of backported it to lambda calculus from linear logic and wrote this very interesting paper. So the claim of this paper is fairly remarkable. It claims that there's some natural extension of, well, both untyped and simply typed lambda calculus in which an arbitrary lambda term has something called a derivative. They prove this extended language, differential lambda calculus, has the good properties that simply typed lambda calculus does, namely confluence and strong normalization. So that's about as good a logical system as you could ask for. So at least from a logical point of view, that derivative of a lambda term, that is of a program, is sort of so it's an object with a good mathematical status. Nonetheless, that's kind of a strange claim, right? That an arbitrary program computing discrete outputs from discrete inputs has something meaningfully that could be called a derivative. So that's a kind of remarkable thing, if you believe it. All right. Okay, so rather than telling you about differential lambda calculus, let me tell you about differential linear logic and what it means for this particular function repeat. Okay, so here's a proof tree in differential linear logic. So this program repeat, which I showed you before, there's a new deduction rule, which is special to differential linear logic, which you can think of as differentiating this program or proof with respect to its input. So now it's got an extra input. Okay, now I'll say what that extra input is supposed to mean in a second, but for the moment, just take its input-output specification as given. And that means I can cut it against two inputs. One is the original S, which, because it's being cut against the nonlinear input, needs a promotion. Now there's another input which is only used in a linear fashion, so it doesn't have a bang on it. And then I cut that in. So this is now repeat. This derivative of repeat takes two inputs, and under the cut elimination rule appropriate to differential linear logic, the outcome is this strange looking beast. So this is now the proof ST of type bint plus the proof TS of type bint. Okay, so in differential linear logic and differential lambda calculus, linear combinations of proofs are also valid things in the language. Okay, so why should you, that's what comes out of the theory. What the hell does that mean? Why should you believe in that answer? Well, it's a very simple calculation that'll convince you why that answer is correct, provided you just buy that all of this has some formal interpretation, and it does. So one can formalize all this so that this calculation is totally legitimate mathematics, but just roll with it for the moment. So take an infinitesimal, and suppose it made sense to vary your original, this is a binary sequence, right? So you take your binary sequence, imagine varying it in the direction of some other binary sequence. So that means taking S plus epsilon times t. And then you want to repeat that thing. Well, that just means squaring it, expand out the brackets, and what you find using epsilon squared equals 0 is this. So what does that say? It says that if you vary the input S in the direction t, the output will vary in the direction st plus ts. That's exactly what the theory computes for you. Okay, so at least in this example, it's kind of doing something reasonable, right? And the claim of Erhard-Regnier is that you can do this for absolutely any proof, at least in simply typed lambda calculus and differential and linear logic. Okay, so
how should I think of ST?
just the concatenation. Yeah. So I just mean, so S is a sequence of zeros and ones, ST just means concatenation. Yeah. Okay, so this is all kind of impressionistic so far because I haven't defined actually what these logics are, but I wanted to get to this slide to show you somehow the idea of what the derivative of a proof is supposed to be, and maybe indicate that it's something that might have some conceptual content that you can easily grasp. Okay, but now let me say what linear logic is. So a proof in linear logic is a tree in which the leaves are all applications of an axiom rule, and the vertices in the tree are instances of these deduction rules. The ones that below the line here, except for promotion. So these guys here should be familiar if you've seen the deduction rules for, if you've seen any sequent calculus, you've seen something that looks like this. So there's a cut rule, a left introduction rule for implication, a right introduction rule for implication. This is currying. This is similar to the left introduction rule for the and this is basically similar to the right introduction rule for, again, and. But these are the special rules in linear logic. Okay, so the structural rules in usual sequent calculus for first order logic have the following two rules. So there's a rule called contraction. Now logically what this says is if you can prove B, sorry, let me use this board over here. So I should have put up the contraction rule for ordinary logic, which looks like this.
These are all multisets, right?
That's right, yeah. So gamma and delta stand for multisets of formulas. And then the turnstile is, if you can prove the numerator in this fraction, so if you have a proof of this, it means you can prove the proposition B using hypotheses of some set of formulas in gamma, some set of formulas in delta, and you've got two copies of this hypothesis. Well, if you can prove a theorem with two copies of a hypothesis, certainly you would believe you can prove it with one copy of the hypothesis, right? We don't go around tracking how many times we use lemmas in our proofs. So that's what's encoded in the contraction rule of ordinary logic. But in linear logic, we say no. You only have the contraction rule for formulas that start with this bang. Okay, so all the formulas are divided into somehow the ones that start with bang and the ones that don't. And you're only allowed to contract on the ones that do. So that means that that rule is actually invalid for many formulas of interest. So you do have to keep track of how many times you use your hypotheses. And moreover, what would this say, the corresponding rule in ordinary logic? It would say if you can prove B not using A at all, well, then you can prove it with a hypothesis A, this extraneous hypothesis. You just don't use it. That's okay. But in linear logic, you're not allowed to do that either unless that hypothesis is prepended with a bang. Now, on the other side of the Curry-Howard correspondence, from the programmatic point of view, this says that you're only allowed to copy inputs which are of type bang something, and you're only allowed to discard information that comes to you with a type of bang something. Right, so that's the content there. The dereliction is the rule that converts you between the two universes, the sort of linear universe and the nonlinear one. So it says, if you can construct a proof of type B, mixing up my terms here. If you can construct a proof of B using a hypothesis A, that is, the way to read that is using that hypothesis precisely once. Well, then you can, of course, construct a proof using that where you're allowed to use that hypothesis arbitrarily, either more than once or not at all. So that's what the dereliction rule says. The promotion rule says, suppose you can prove A, and everything on the left-hand side of the turnstile has a bang in front of it. Okay, so gamma is some multi-set of formulas, and they're all starting with a bang. That's what that notation means. So if you can prove A, where all the hypotheses can be used arbitrarily, well, that means that you can prove A as many times as you like too. Right? So you've managed to get a proof of A using 2 copies of the first hypothesis, 3 copies of the second hypothesis, and so on. And then you want to prove A twice. Well, you use 4 copies of the first hypothesis and 6 copies of the second hypothesis, and so on. right? So that's the idea behind the promotion rule. Okay, so the deduction rules of linear logic are basically constructing programs, if you like, which are managing their resources, and where only resources prepended with a bang can be used in an arbitrary way. Okay, so here's an example. This is the encoding of the sequence 001 as a proof of this type. And, well, I don't necessarily want us to stare and understand all the details of this proof tree. But the one thing that maybe is worth noting is that you see in this last step there's a contraction rule. And that's contracting these two copies of bang A implies A. And that corresponds to the fact that 0 is repeated. So there's some pattern of contractions which corresponds to the actual digits in your sequence. So that's the idea behind how you encode a sequence of zeros and ones. Okay, but it's not too important that you sort of understand all the structure in that tree. So since Rajiv already mentioned somehow, I mean, in his proof trees there were terms, right? So these types were decorated also with terms. I'm not doing that anywhere here because that's not typically the way I think about things, but that's what these two boards are for. So these two boards actually contain the term calculus annotations of some of these proofs in linear logic. And you can see somehow appearing in those terms things like copy f as f prime f double prime. That's the manifestation of the contraction rule in the term calculus, and there's also derelictions in the term calculus. So there's a I mean, you can write linear logic down as an actual programming language, and it contains these contractions and derelictions as actual sort of instructions. Okay, there's the proof tree for repeat. Yeah, maybe here again, the only thing you should pay attention to is the very bottom. So what's the first thing that this program does? It takes its input and it copies it. Right? So this is the thing coming in here is the S, and it gets copied to 2 copies of S, and then something else happens. Okay, so that's so proofs in linear logic are these trees constructed from these deduction rules, and then there's some equivalence relation between those proofs given by cut elimination. And a semantics of that logical system is some assignment of types to mathematical objects, proofs to some transformations of those mathematical objects, in such a way that 2 proofs which are equivalent under cut elimination go to the same transformation. And maybe one of the most elementary semantics of linear logic is defined in the following way. It's just basically in tensor algebra or linear algebra. So the way this works is that so this means the semantics. LL stands for linear logic. Vect K is for vector spaces, let's say over C. Every type goes to some vector space, obeying the following rules. So the linear implication gets mapped, so A, lollipop B. Its denotation is the set of all linear transformations from the vector space associated to A to the vector space associated to B. That's what Hom K just means, linear transformations. So if you like, that's a space of matrices. The denotation of this tensor product is just the tensor product in linear algebra. So that has a dimension which is the product of the dimensions of A and B. But this is interesting. Okay, so this is the place where something sort of non-trivial happens. Okay, so what do I do with things that start with a bang? Well, suppose A is finite dimensional. Suppose it has dimension n. So sim A, what that means is the polynomial ring generated by n variables. Okay, so sim is some construction you can do to any vector space. If you put in an n-dimensional vector space, it spits out something that is isomorphic to a polynomial ring in n variables. And then you take one copy of that polynomial ring for every point in your vector space. Okay, so that's basically, I mean, given what I said about K, this is definitely an infinite dimensional vector space that's getting assigned to this bang. So this is something complicated.
So this is before linear logic, right? He was at the
Sweedler? Yeah, that's right, yes. So Sweedler, yeah, the reason, so this is, This is my name for this semantics. So I named it after Sweedler. No, it's so the reason I call it the Sweedler semantics is this thing. I mean, who would just write this down? It's not just you chose this particular strange combination of vector spaces. This has a universal property. It's a co-commutative coalgebra which is somehow universal with respect to having a linear map to this vector space A. And Sweedler was the person who studied such coalgebras.
Yeah, I know him.
Oh yeah.
He's still alive, you know?
I've never met him.
He's nice, man.
Yeah, so he has a very beautiful book called Hopf Algebras, which is
What's the plus again, please?
Plus.
Oh, plus.
This one. Oh, sorry. Yeah. So this means I just take a direct sum of copy. So if I take two vector spaces, so if it was just V plus W, this just means the vector space whose vectors are pairs of a vector in V and a vector in W. So this is a coproduct. It just means, so the vectors in here, if you like, are sequences. Well, they're tuples of vectors indexed by P, where all but finitely many vectors are 0. So the idea is that this co-free coalgebra is somehow the structure which takes vectors in a vector space and sort of allows them to be copied arbitrarily in some universal algebraic sense. So, I mean, this is sort of the details of how the algebra, or rather coalgebra, works, but maybe I won't say much about that. Okay, so maybe the point I want to make in this talk is to convince you that this idea of a derivative of an algorithm isn't crazy. Well, clearly it's not crazy, it's published and it's in a good journal, so it's in some sense not crazy, but okay, maybe it could be that differential lambda calculus or differential linear logic is some well-behaved logical system which happens to have some operation that you can call differentiation, but maybe that's just some peculiar logical thing, and maybe it doesn't have a lot of conceptual content that you can grip onto, right? So I want to convince you that in fact there is a very strong conceptual idea behind there that you can grab onto, and this complicated diagram is meant to indicate how I'm going to do that. So, well, one of the reasons it's hard to sort of intuitively understand what the Erhard-Regnier derivative is doing is that lambda terms are a bit hard to understand too. So let's take Turing machines, which we can have some mechanistic idea of, encode them into lambda calculus or linear logic, and then differentiate them. Okay, so what does this mean? So this encoding here is, I mean, of course, Turing himself in his original paper wrote down an encoding of Turing machines in lambda calculus. That's in the appendix. And then Gerard in some work on, actually, the early work on complexity in linear logic, wrote down an encoding of Turing machines into linear logic, which refines that encoding of Turing's. So you can take a Turing machine, you can encode its sort of n-step transition function as a proof. And then you can apply this, I mean, so then you've got a term or a proof in linear logic. You can differentiate it inside this bigger language, differential linear logic. And then you can say, well, what is that thing? Well, it's just some term in some language. I mean, it's just sitting there. It's just some proof tree with a funny delta at the bottom. Well, that's what semantics is for, right? The point of semantics is to take some complicated logical object and actually extract something from it which you can maybe look at, maybe some numbers, and actually understand. So that's what we did. So this arrow here is the Sweedler semantics using these coalgebras. So that's a semantics of linear logic, but it extends naturally to a semantics of differential linear logic for the reasons I kind of alluded to, because this coalgebraic language already somehow knows about derivatives, and at its root that's because of Gerard's comment in his paper, right? He observed that somehow there's this connection between substitution and derivations, and as I said, that's familiar to any algebraic geometer, and that's actually the same reason why these co-free coalgebras somehow already know about the differential structure in linear logic. So you can take this semantics and then you can just stick in your derivative of a Turing machine and see what you get. Right? Okay, so then the question is, well, what is it? What does that derivative compute? Okay, so I claim it computes rates of change of a certain kind of probability. That's the upshot. I can't see a clock anywhere. Let me just...
It's another 25 minutes to go.
25, okay, that's plenty. All right, so I'm going to step back a bit and just talk about probabilistic Turing machines, but let's keep that question in mind. So we have this derivative of a Turing machine, and we can apply the semantics, and now I'm going to tell you over several slides what the answer is. Okay, but before I want to give you some context for that answer. So consider the Turing machine, which just swaps its inputs. It just starts at some position, moves to the right, and swaps every 0 for a 1. Okay. Well, now there's, of course, a well-defined notion of a probabilistic Turing machine, which has transitions which somehow have a stochastic nature to them. But that's not quite what I mean here. So this picture is meant to indicate probability distributions over bits. So let me now consider where instead of having certainty that it's a 0, 1, 1, 0, now I'm certain it's a 0. There's a little bit of uncertainty about whether that's a 1. I'm certain that's a 1, and I'm certain that's a 0. Well, if I sample from those distributions of bits and feed the samples through my Turing machine and then accumulate the results, what I'll see is that I've propagated that uncertainty to uncertainty about the output bit in the second position. Right? Okay, so if I like, I mean, that's a continuous process, right? As I vary that uncertainty is going to vary smoothly. So I can look at the derivative of, so y here means the probability of seeing a 0, x here means the probability of seeing a 0, and the derivative of that y with respect to that x is minus 1. Okay, so that's kind of a derivative of, propagating uncertainty through a Turing machine, but it's uninteresting. Why? Well, because it didn't matter what the actual algorithm was, right? Any algorithm that outputs 1001 on that input will have the same behavior with respect to propagating uncertainty, because if I'm propagating uncertainty, I just sample, I feed it through my machine, and I accumulate the outputs. I don't care what the machine does or how it works. I just care what the input-output behavior is. So propagating uncertainty in this way, using standard probability, will never give you any interesting notion of a derivative. Okay. But nonetheless, I claim that there's some kind of non-standard way of propagating uncertainty through an arbitrary Turing machine. And that is what the Erhard-Regnier derivative is talking about. Now consider, I've got some input bits. So these are distributions over 0 and 1. Let x, as before, be the probability that the second digit is 0. Y, as before, well, so now I'm claiming there's some way of propagating uncertainty through the Turing machine. I won't give you the formulas. I mean, they're in the paper, obviously. I'll just tell you where the formulas come from. Well, you take the Turing machine M, you encode it into linear logic, and you look at its semantics. Its semantics is some linear map between coalgebras. You look at that linear map, and what it gives you, the information in that linear map that the semantics gives you for that Turing machine, is actually the information for how to propagate uncertainty in this strange way through your Turing machine. So I'm not going to, as I said, not going to tell you the nitty-gritty of how that propagation works, although do ask me if you're interested. But when you do that, what you can check is that the rate of, it's a smooth function. So still this y, this is no longer the result of propagating uncertainty through the Turing machine according to standard probability, but it's some probability distributions you get out the end. And if you look at the probability of that second digit being a 0, it's again a smooth function of x, and the derivative is some number, it's an integer. And that's exactly what the Erhard-Regnier derivative of the step function of the encoding of M is doing. So in the logic, there's some coefficient of an integer. As I said, the proofs in differential linear logic are linear combinations of terms. So you get some integers, multiplicities in those terms. And those multiplicities are exactly these rates of change. Okay, so that's what comes out of the analysis using the semantics of what the derivative of this encoding of a Turing machine is. Okay, so that's one reason, I guess, to believe. And I was going to say to believe in the Erhard-Regnier derivative, but I mean, of course, the paper convinces you this thing exists logically, but this is maybe some intuitive message for what it is talking about. Right? And what's the idea here? Well, the idea here is, why do you think an algorithm computing discrete outputs from discrete inputs can't be differentiated? And it obviously can't somehow, right? Because what's the derivative? You take an input, you're supposed to vary it infinitesimally and measure how the output varies and measure the ratio of the variations, right? If you can't vary the input infinitesimally, the derivative shouldn't make any sense. So therefore, of course, programs can't be differentiated. What's encapsulated by that formal notion is, I would argue, at least for this class of proofs, the conceptual idea that, in fact, you can vary a discrete input. Right? You just vary it within probability distributions. That's a standard trick, right, in discrete optimization problems, for instance. So that's a totally reasonable thing to do. The trick there is you just need a sort of novel way of propagating that distribution through your discrete algorithm. But that exists, and that's what differential linear logic somehow gives you. So the second part of my title was about proof synthesis. So here's an idea for generating a proof or a program subject to some constraint, and the constraint is of this kind. So suppose I have input term of type A and an output term of type B, and I want to find a program pi which maps U to V. Okay, so this is basically one formal way of saying what the problem of inductive inference is, right? I give you a bunch of observations of certain causes and certain effects, and I ask you, what is the generating process for all those pairs? And if I imply some kind of regularization like Occam's razor, then I want the shortest explanation with respect to some measure of complexity, right? So that's somehow what I'm getting at. Now, you could ask this question for arbitrary types in linear logic, but let's just consider it for the particular case of encodings of Turing machines, where it takes the following form. So I can encode a universal Turing machine into linear logic, and that program in linear logic will have two inputs. One is an input sequence, and another is a code of the Turing machine I'm supposed to simulate, and it will give you the output of that Turing machine on that input. So then this problem phrased for Turing machines is, if I give you a bunch of input sequences and the corresponding output sequences, tell me the code of the Turing machine which generates those outputs on those inputs. I mean, of course, there's infinitely many, but maybe give me the shortest one. Now, that answer also depends on the choice of universal Turing machine. Of course, there's many essentially different universal Turing machines in terms of giving the answers to these kinds of questions. But if I fix U and I say, give me the shortest one, well, at least there's only finitely many possible answers. Okay. So that's what I mean by proof or program synthesis. Generate the code which explains a given set of input-output pairs. So the idea here is that using the ideas I just explained, and essentially just using the idea of the Erhard-Regnier derivative, you can construct a smooth function on this hypercube whose global minimum is a solution to that problem. Okay, so what is this hypercube? Well, suppose I restrict to sequences of n bits. And then I look at probability distributions over each one of those bits. So this is n distributions over 0 and 1. Okay, and I just explained to you, you can propagate uncertainty through any proof, in particular through the encoding of a universal Turing machine. So if I give you a fixed input and an uncertain code, you can propagate that pair through your universal Turing machine, and you'll get some uncertain output. So here's the idea. So here's my UTM tape. There's a code. I'm not sure what the code is because I'm looking for the solution to this problem, but I know what the input is, and I know what the output I expect is. So I can take this sequence, which has uncertainty in it, I can propagate it through the universal Turing machine for some number of steps. This is kind of an important restriction here. I need to decide ahead of time the number of steps. Okay, so this, if you like, is quite a restriction. So once you know, that's part of the problem description, therefore, right? I give you inputs, I give you outputs, and I say the Turing machine I'm looking for will compute that output within TI steps on that input. Okay, so given those triples, x, y, t, then you know to propagate the uncertainty for t steps. This delta just means this propagation of uncertainty through the step function of the universal Turing machine. You get some tape which has uncertainty on it, and then you can measure the distance between that sequence of distributions and the true output. And there you just use the cross entropy or KL divergence, which is this quantity. Okay, so that's a standard measure of distance between distributions. And that gives you a loss function, right? So your true Turing machine, which solves this problem, will have distance 0 for all those pairs. So then you've got a function, and you try and minimize that by varying this code over this space. Okay, so this is the kind of cartoon, right? So you start at some initial value of those distributions, and then you just do gradient descent against that loss function, and theorem, the global minimum, there's only one, and it's the solution. Okay, so that seems like a kind of neat, abstract way of synthesizing a Turing machine. I mean, it doesn't work. I mean, well, it works in some sort of very simple cases. So you can synthesize this swapper machine that I described to you. If you look at this, so this is the graph of the loss of this function against, this is not literally 2,000 steps, it's times 10 to the 3 or something. So you can actually do this gradient descent. So we wrote this up in TensorFlow, and it solves the problem for this swapper machine. So if you take all Turing machines which have, I think, an alphabet of 3 and 2 states, there's like 260,000 or something of them, and then you just do this gradient descent and it will spit out the solution. Okay, so, you know, I mean, maybe what's the point there? The point is somehow that you can actually code up this propagation of uncertainty through a universal Turing machine on today's computers. It's not some crazy, like, super complicated thing. So, I mean, I think this runs for like 50 steps or something. And what this graph here is showing you there's 18 variables because, well, so you've got 3 symbols and 2 states. So that's 6 tuples in your Turing machine, and each tuple has 3 undetermined bits in it. So that's 18 bits. And, well, there's some crazy dance as the bits change around here. The higher this is, the more uncertain you are about the value. So it starts off very uncertain about almost all the bits, and then some crazy dance happens, and then it's sort of solved the problem. And this picture here is the actual values of some of these bits. Okay, so this is kind of it's an interesting angle on a problem that's been approached from many different points of view in recent years, which is the idea of synthesizing programs by gradient descent. And nobody can make this work, and there's a good reason for that. Basically, in all the papers that try and do this kind of construction, what you find is that the loss landscape just has tons of local minima which are not actual solutions, so they're not global minima. And that's true in our case as well. So basically the loss is sufficiently informative in terms of having a good gradient flow to a global minimum in very trivial cases, but if you try and synthesize complicated Turing machines this way, it just always gets stuck in local minima. I think that's probably some manifestation of the no free lunch theorem, but I don't think anybody has a good theoretical explanation for that yet. Nonetheless, empirically, that's what everybody seems to find. So these two papers, yes. So this is a very interesting paper. This is not propagating uncertainty through a universal Turing machine, but it's like the logic programming equivalent. Right? So if you've done logic programming, you know that there's some backward chaining or forward chaining. So you have some sort of backward chaining engine, which is the analog of universal Turing machine, and you can propagate uncertainty through that and then do a cross entropy to get your loss. That's exactly what these guys do. Now, so they have to choose some way of propagating that uncertainty, right? So it's quite amusing that the exact method they used to propagate it, I mean, they just came up with it, is exactly what somehow linear logic wants you to do. So if you like, what I've described to you is some theoretical justification for that ad hoc choice of propagating uncertainty that people have come up with. And these guys had exactly the same choice of how to propagate uncertainty. I mean, to summarize, I think, as I said, two of the deep concepts that computer science has contributed, computability and complexity. I think it's possible that differentiability of algorithms could eventually be a third. I think it's too early to know if that's the case, but I think proportional to how certain I am of that, very few people are aware of Erhard and Regnier's work. So I think this is very important work that deserves to be better known. And at least in these cases, I mean, I actually don't know what the derivative of a general proof in linear logic means from a probabilistic point of view. So maybe I wasn't careful enough when I described it, but what we calculated was that in the case of the encodings of Turing machines in a sort of slightly broader class of proofs, which we call plain proofs, the Erhard-Regnier derivative does compute these rates of change of naive probability, as we called it. For general proofs, I don't know if that connection still makes sense. But in any case, I think there's some interesting connection between propagating uncertainty through algorithms and these Erhard-Regnier derivatives. Yeah, and maybe one day you can use that to do proof synthesis, but not right now. So I'll stop there.